Hi, welcome back. In this lecture, I want to introduce the HHL algorithm, that is a quantum methodology and technique to solve a linear system. In this lecture, we're going to use a concise way of representing a system linear equation, such as the one presented here, that is using a matrix or tensor formulation. It turns out that a linear system comprising, for instance, here, two equations can be concisely written in this form here. So each coefficient of x1 and x2 will correspond to a line of our tensor. So in this case here we have 3 and 4 will be the first line, here and here. In this case, in the second line will be also populated the second row of the matrix. So we have 2 and 1 here, and this we're going to put it here and here. We also have the right side, hand side of the system linear equation, and this we will store in a separate vector, that's typically called b, and this will be having 3 and 3 that will go in the different row of the vector b. So given initial system linear equation, we can cast it in a tensor or matrix multiplication of matrix A, that is taking the coefficient of the system linear equation, the unknowns, those are the solution of the problem that we want to solve, equal to the source term, that is b, that is the right hand side of the equation we want to solve. So a system of n linear equation for n variable, x1, x2, xn, can be written as a matrix equation containing an n times n matrix A and an n-dimensional source vector called b. So in the previous slide, we saw how to cast it as linear system equation in this formulation. So A matrix, X is a vector with our solution, and B is the known term. It is also the right hand side of our system linear equation. So how do we solve this linear system equation? That means how do we find the components of the vector X, which is our solution? Well, the task of solving of the system equation boils down to being able to invert the matrix A. So the most difficult part is going from A, calculate the inverse that we can call A to the minus 1. Once we found this A to the minus 1, we can simply calculate the solution, which is our vector X, by multiply A to the minus 1 by B. So it boils down to calculate A to the minus 1. That is the most difficult part of the problem, of the solution of a linear system. So when we want to solve a linear system, what we're going to look at is going to look a way to calculate it to A to the minus 1. And that's what also the quantum algorithm is going to do. This lecture is focusing on the quantum version of a linear solver that goes under the name of HHL, from the names of the people who discovered this algorithm. HHL stands from Harrow, Hasidim, and Lloyd, who are the people, the scientists who introduced this algorithm. This algorithm is using a bunch of different quantum algorithms, for instance, using the quantum phase estimation to find the matrix inverse. And this is going to do that in a faster way than other classical linear solvers, such as the CG or conjugate gradient linear solver. In reality, the HHL solves a distinctly quantum version of the problem. And why I'm saying a different version of the problem? Well, we see that the HHL algorithm uses amplitude encoding both for the source term, but also for the solution. So our solution of the problem will be encoded using the amplitude. And as we saw at the beginning of this module, what are the disadvantages of amplitude encoding a vector? We saw that the solution will be amplitude encoded and will not be the exact solution of our problem. It will preserve the global structure of the solution, but there will be a difference of a scaling factor. Remember about the normalization of amplitude encoding. So this is a slightly different problem, because we will find a solution, but it will be amplitude encoded. And the other way, the other issue will be that will be in amplitude encoded. These are the different components of the HHL algorithm and a quantum circuit. I want just to say a few things. Well, first thing that, as I mentioned before, we are going to use amplitude encoding of B, and therefore we might need to have a QRAM. So we have a superposition of different addresses in memory that will allow us to retrieve a vector in using the quantum state and the amplitude encoding. We also are using a solution register where the solution of X will be also amplitude encoding. We also need a quantum simulation approach in order to encode the matrix A. So if we have a matrix that is A, which is Hermitian, right? This will allow us to a process of exponentiation to express it in terms of unitary matrices and therefore gates. There are a bunch of quantum registers and that we're going to look at into detail in the next lecture. We have a scratch register that will contain different values for allowing different primitives within the HHL, and this will be prepared in the state 0. A point that I want to make is that we are going to use a fixed point data to encode the solution, and therefore this might require quite a few of scratch qubits. I already mentioned that our B will be amplitude encoded, and therefore we might also need the QRAM if we want to have the usage of different quantum state to encode B. I also mentioned that A, our matrix A, will be encoded using the quantum simulation approach. We can start from a generic matrix A, we can make it Hermitian. Once it's Hermitian, we can use an exponentiation process to express it in terms of quantum gates. So all the matrix A must meet all the requirements that we noted for performing the quantum simulation. The output of the HHL algorithm will also be amplitude encoded, and also this implies that we cannot assess individual solution directly, but this will require several measurements. And also the scratch register will also put it back to the initial state, so we can continue using SLR in our quantum computing system. What are the applications of HHL? So HHL algorithm is in many cases quite useful. For instance, if you want just to calculate the derived property, such as the sum, the mean value, or it contains a certain frequency component, we can use the swap test if you want to check whether or not the solution vector X is equal to one particularly suspected vector that we expect. Also, it is worth to mention that the HHL algorithm is an important component in a larger algorithm. For instance, it's widely used in machine learning. If we want to do principal component analysis, typically the HHL is a starting point for many of the quantum machine learning applications, including regression and data fitting. I want to finish up this lecture by talking about the complexity, about the algorithm. The complexity of the HHL algorithm depends on four major factors. The most important one is n, that is the size of our matrix. You see there is a complexity of a big O or log n. So that's the important part. So increasing the size, the complexity is a big O of log n. There are the other three factors here. One is the condition number that is defined as the largest eigenvalue of the matrix A over the smallest eigenvalues of the matrix A. And this is important for the convergence of to the solution. We also have the sparsity, that is the number of zero element. So the higher the elements are zero, the higher is the sparsity. And then there is a part on how much precise is the solution on X. And we are using epsilon that we saw before in the quantum phase estimation. Remember that there was some parameter that we decide that was determining also the precision. It turns out the HHL algorithm using the QP, and therefore also we have the parameter about the precision. So how the different classical linear solver works? Well, if we want to do like a direct solution, most of the methods are and cube. So this is quite complex operation to do the inversion. If we use some iterative solvers such as a conjugate gradient, then the complexity goes quite low. For instance, in the case of conjugate gradient, the complexity become linear in n. So it is big O of n. And still, these are the parameter, the sparsity, the condition number, and the precision. So what we are going to compare here, the quantum and the classical case, is these two different factors. So in the case of the quantum version, we have a big O or log n. In the case of one of the best classical methods is the CG, iterative solver, and this will be big O of n. So the quantum version clearly offers an exponential improvements when compared to the classical case. We also note that the dependency of the computational cost on the sparsity and the conditioning of the matrices. So the HHL algorithm also works quite well when the matrices are quite sparse and well conditioned. This is the last slide of this lecture, and talk to you soon.